Hi there. Today we're going to be doing some partial fraction decomposition in this little tutorial here. So first, what you're going to need to do partial fraction decomposition, or PFD as I like to call it, is you're going to need a higher power polynomial in the denominator than in the numerator. And this can be seen in the first of three examples that I'll be showing today. So the first, you can see that the bottom is a quadratic, or a degree 2 polynomial, and the top is just a single number. So the bottom, the denominator, is definitely a larger power than the numerator in this case. So first what you're going to do is factor the denominator. So here you can see I've just basically split up this x squared plus 3x plus 2 into an x squared plus 1 and an x squared plus 2. The next step you're going to want to do is split up that fraction. Now, what you do here is you assign a variable, usually a capital letter starting at a, to the first half of the fraction. So it would be a over x plus 1 plus b over x plus 2. And that equals the right hand, or the numerator of the fraction. And this is shown here. So basically what we have is we've split it up, and we have to find a common denominator. So now what we're going to do is multiply everything by x plus 1, x plus 2. So it's all being multiplied in, and then what you do is you cancel your terms. So here you can see what's been canceled off, and what you are left with is something that is a lot simpler with no denominators, and it's just a single line. Now you can see our unknown a is next to x plus 2, and our b is next to our x plus 1. Now those are multiplied together, and they both equal the numerator as previously stated. So what you're going to do with that next is you're going to evaluate the terms. And now what evaluating the terms is going to do is it's going to give you those unknown coefficients, those a and those b, to figure out how you can split up the fraction properly. So first what you're going to do is you're going to evaluate x as if it were to be a negative 1. And the reason I choose this is because, as you can see in the b portion of the equation, that'll send that right to 0. So then you have one equation, one unknown. So you can see in my line of math there, it's a with the input negative 1 plus 2, plus b with the input negative 1 plus 1, which ends up going to 0 as seen in the next line. And that equals the right-hand side, or the numerator of the fraction. And if you do your math and go through, you figure out that a equals to 1. Now, what you're going to do is you're going to choose x as if it were to be negative 2. And in doing that, you're going to set a to 0. So then you're going to have one equation, one unknown, but in this case, it's just with b. So you can see I've put in a, the input number 2, negative 2, plus 2, plus b, the input negative 2, plus 1, again equals 1, or the right-hand side of the equation, or the numerator. The a goes to 0 in the second from the last line, and it's negative b equals 1, so therefore b equals negative 1. And there's our original fraction that we originally split up, and since a equals 1 and b equals negative 1, you now know that our original fraction, which was 1 over a quadratic, equals 1 over x squared minus, 1 over x plus 1 minus 1 over x plus 2. And that's a very simple partial fraction decomposition with a single number on the top and a quadratic on the bottom. Alright, so next up is our example number 2. And example number 2, what it includes is, instead of just having linear components on the bottom, it's now going to have a quadratic component on the bottom, and also it's going to have a polynomial on the top as opposed to just a number 1. So as you can see here, our original question would be something like x plus 1, a linear, over a cubic, and that would be x cubed plus 2x squared plus 2x plus 4. Now again, you're going to factor the denominator just as before, and the numerator remains x plus 1. The denominator now becomes x squared plus 2 multiplied by x plus 2. Now, again, same as before, you split up the fraction. Now it's a little bit different because the rule is, when choosing your variables for the numerator, is that they need to be 1 power less than the denominator. Now, in the case before, where the denominator was x plus 1, we simply just put an a, because something less than a single exponent polynomial is just a number. Likewise, in this, a quadratic, as seen in the left-hand side of the equation, has to be paired with a linear in the numerator. And much like before, the x plus 2 in the denominator is paired just with a single number because that's one less power than an x to the 1. So again, we split up the fraction and we multiply through by a common denominator. And I haven't shown all the work here this time, but that's what results from that. Following this, we again cancel the terms that are similar. And as you can see, they clean up very nicely, and we're actually left with something that looks like this. So we have a linear ax plus b multiplied by a linear x plus 2. We have a single number c, some number c, multiplied by a quadratic x squared plus 2. And again, this equals the right-hand side, or the numerator of the fraction, in this case x plus 1. So we're going to evaluate the terms much like before. I want to choose terms that make whole portions of the equation go to 0. So I'm going to choose x equals minus 2 for simplicity, because as you can see, when we plug that in, it becomes negative 2a plus b multiplied by 0. So essentially a and b just go away. And then we have negative 2 squared, which becomes 4, plus 2, which is 6. The right-hand side of the equation is now as if it were negative 2, which is what we input, plus 1, so negative 1. So therefore c equals negative 1/6. And it's that simple. Now the next evaluation we're going to do is x equals 0. And now what x equals 0 does for us is it actually removes one variable but leaves in b and c. Now, this is good because we've already found c, so technically we just have one equation with an unknown b. So plugging in 0, we have a times 0, gets rid of our a, plus b, essentially multiplied by 2, since we've added a 0, then plus c squared plus 2. So it becomes multiplied by plus 2, sorry. So the equation just becomes 2b plus 2c equals 1. Now we know that c, as what we found before, is negative 1/6. So plugging that into the brackets as you see there, and following through with our math, bringing the 2 inside the brackets becomes negative 1/3. Bringing that to the other side and then dividing by the 2 out front of the b, we get b to be simply 2/3, which is a very nice number for us because the last one was 1/6. They're pretty similar. Now, this is a little bit different how we're going to evaluate these terms. Is what we're going to do is we're going to try and find all the terms that have x squareds, and we're going to group those together. So to do this, we want to expand our equation that we found once we canceled our terms. And in that expansion, we're going to have ax squared plus 2ax plus b plus 2b plus cx squared plus 2c equals, again, x squared plus 1, which is the numerator of our original fraction. Now, looking at that equation, we notice that there's only two terms that have an x squared, and that's a and c. And on the right-hand side, there's no x squared, so we're going to put a 0. And again, we know our c term, which is negative 1/6, so if we say a plus c equals 0, that means a minus 1/6 equals 0, so a simply equals 1/6. Now we found all of our unknowns, a, b, and c, and we take our original equation as shown here, and we know that a is 1/6, b is 2/3, c is minus 1/6. So therefore, our original equation, which was a linear over a cubic, or you can see the factored version here, simply equals 1/6 x plus 2/3 all over x squared plus 2 plus 1/6 divided by x plus 2, or as I have written here, 1 divided by 6 times x plus 2. They're both the same. They're both the same thing. So that's how you would do it if you have a linear on the top and something greater than a linear on the bottom, and how you would deal with associating the variables, as in putting ax plus b over something that was an x squared plus 2. So remember, always one lower power than the in the numerator than in the denominator when solving for your unknowns. Now, the next example is example 3, and this is what we call our repeating case. And it'll be illustrated here in a second. So first of all, you have a 1 over x squared multiplied by x plus 1 all squared. Now, you may be tempted to write your unknowns as over the x squared as ax plus b, because you think the x squared, okay, it's a quadratic, I need to have one less power. Now that's not the case. It can be done that way. It's a lot of extra math, but it all works out the same. Basically what you want to do is you want to do this. So you want to put an a over the x squared, and since it's repeating, as I mentioned before, then you just go drop down the power and you say b over x. Then you go c over x squared plus 1 all squared. Again, it's repeating, so you again do a linear, or assume it's a linear, and you put a c above it. And then you go d over x squared plus 1, which is the repeated of the x plus 1 all squared. Now that, again, just equals the same fraction. So it's a lot easier to deal with 4 single terms, a, b, c, d, than it is to deal with above that x squared, ax plus b, and then above that c, cx plus d. It's a lot easier to deal with simply 4 linears, and you'll see why in a second. There's a lot of mirrored answers and with simple sign changes and such like that. So here you can see what I've done is I've actually multiplied through by a common denominator and canceled the terms already, and that's the line that we come up with. Now it seems a little bit hairy off the start, but you'll see it turns out to be rather nice. We're going to evaluate the terms, just like always, and I'm going to try with an x equals minus 1, and again, doing that, it sets a lot of them to 0. And that's what we want. We want to get rid of a lot of terms right off the start so we can simply find the ones we need. So plugging in an x equals minus 1 into the a, b, and d section, they're associated with an x plus 1. So that's going to set those to 0, and c therefore equals 1. Now I'm going to again do x equals 0, and that's going to get rid of a few because they share a term, either x or x squared, so plugging in a simple x equals 0 gets rid of them completely. And since a lacks that x or x squared, a equals just the 1. So again, a equals 1. Now we're going to keep going, and we're going to do much like we did in example 2 and evaluate the x squared terms. Now what I've done is I've expanded it out and just listed the x squared terms here for you. So you can see the x squareds are a, 2b plus c plus d equals 0, since the right-hand side, or the numerator of our original fraction, doesn't have an x squared. Now again, we know a and we know c to be 1, so we can plug them in and find that 2b plus d equals negative 2. Now in the square brackets I've put a 1, and we're going to list that as equation 1. Next, what we're going to do, which is a little simpler, is we're going to evaluate the x cubed terms. Now again, I've done the expansion and only shown the x cubed terms here, and they are bx cubed plus dx cubed, again, equals 0, because the numerator of our original fraction did not have any x cubed terms. So we can simplify that as b plus d equals 0. Now that's equation 2. So what we're going to do is we're going to associate equation 1 and 2, rearrange equation 2 to be b equals minus d, and you can see below that is simply just equation 1. I've plugged in b equals minus d into equation 1 to find that minus 2d plus d equals minus 2, and that simply is d equals 2. And since we know b is negative d, we know b is negative 2. So again, we have our original equation shown in the top line, and that a equals c, which equals 1, b equals minus 2, and d equals 2. So therefore, our repeating case equals the last line there. And that's as simple as it is. When you have something that is simply an x squared on its own, you can treat it as a linear, but you have to treat it repeating. You have to have the x squared followed by the x. If it was an x cubed on its own, it would be x cubed followed by x squared, again followed by x. Now I hope these partial fraction decomposition tips have helped you out, and let me know if you have any further questions. Hope you have a good day.